We're going to look at the radian measure and also angular speed, which is connected to the idea of a radian measure. You may have met the radian when you're looking in your normal pure maths in trigonometry. So we're just going to talk a little bit about that. So the radian measure is a different way of measuring an angle rather than using degrees. You know that 360 degrees is a full turn. You also know in terms of a circle that the circumference of a circle is 2 pi r. So whatever the radius is, you multiply it by 2 pi, which is approximately 6.28. If you multiply the radius by 2 pi, you get the distance around the outside of a circle, the circumference. Now, a radian, as its name is, as it suggests, a radian is the idea of a radian is connected to radius. So if we imagine a length that's equal to the radius, and we were to curve that up against the arc, okay. So that red line there is the same length as the radius. If we were to make an angle subtended from the ends of that arc, okay. We would make an angle at the center there, and that angle at the center is equal to 1 radian. So 1 radian is equal to the angle, or the size of an angle that is created when you have any circle, an arc of length equal to the radius. And if you think then, how many of these can you actually fit in? Well, if you think about the fact that you can get 2 pi, lots of radius, around the outside, we end up with just a little bit more than 6 of these arcs, as 1, 2, 3, 4, 5, 6, and another just over a quarter of a radius length there. So there's 6.28, i.e. 2 pi radiuses around the outside. Okay, and in terms of the angle, there are 6.28, i.e. 2 pi, lots of radians in terms of the size of the angle. So 2 pi radians is the full turn, i.e. 360 degrees. We can then start making connections between radians and degrees. So if we think about the circumference of a circle, we know that its circumference is 2 pi r. If we want to think about a part of a circumference, a length, we can think of that in terms of my angle. In terms of 2 pi, okay, is the full turn in radians. We can take any angle in radians and multiply by the radius. Now that's more commonly written, you can see in the formula book. Okay, length is radius multiplied by the angle in radians. So it's just the other way around, the same idea. We can also rearrange this equation to make the angle the subject, and we can have the length of any arc divided by the radius, okay, and that's equal to the angle in radians. So the length of the arc divided by the length of the radius. We can appreciate that in terms of radians, 2 pi radians is equal to 360 degrees, or pi radians is equal to 180 degrees, and then we can then look at other angles. So for example, 90 degrees is pi over 2, and other ones such as 60 degrees is pi over 3, and pi over 6 is 30. I suppose I shouldn't forget pi over 4 is 45 degrees. So they're the standard conversions, and you can effectively find them actually all in the formula tables book within the table of sine cos tan ratios. So we have 2 important just formulas, I suppose. Length equals radius times by the angle in terms of radians, and if you rearrange that, we've got the angle in radians is equal to the length of the arc divided by the radius of the circle. They're 2 useful formulas to have. One's given to you in the form of a book, the other one can be found just by rearranging it. So let's just say, for sake of argument, I have a circle with a radius of 5, and I've got an arc length that happens to be, 9. Then we can say that the angle that's created from that arc of 9 is going to be 1.8 radians. If we had a radius of a circle of radius 4, and let's say we had an angle of, let's say for sake of argument, 3.2 radians. It's a little bit more than 180 degrees. Then my arc length is going to be 4 multiplied by that angle in radians, which is going to be 12.8 units long. So if this was in meters, then that would be 12.8 meters long in terms of this length of the arc. Now let's look at one application of radians. So here we've got, imagine this a roundabout in a playground, and you've got 2 people on that roundabout. One person sort of not in the center, but sort of not on the outside, or on the outside, okay? And let's say that the radius of this roundabout is 9 units, and then the person slightly inside, hanging on into a seat on the smaller, further in, is only 5 units from the center. So if we think about those 2 people, what's the speed that they're going at? What's the speed of the roundabout, I suppose, is one thing to think about, but also separately, what is the speed of the 2 people? Well, one revolution of this animation is approximately 9.5 seconds. Okay, so we can start talking about the speed of the roundabout. We can also talk about the speed of the 2 objects. Now, the person on the outside, the one that's 9 units away from the center, is naturally going to be going faster than the person who is 5 units away. And the way we can think about that is in terms of the distance traveled. So think of the person who has a radius of 9 away from the center. If they're doing a full turn, okay, that's the circumference is 2 pi times by 9, which is 18 pi, which is 56.5 units. That's the distance they're traveling around the outside. Okay, and I told you it's taking about 9.5 seconds. So the velocity, okay, is just going to be distance divided by time. So if we think about the 56.5 and divide it by 9.5 seconds, let's imagine this was meters, okay? Let's talk about units. That would be 5.95 meters per second, almost 6. Okay, I think there's a bit of rounding going on here. It might just be 6. If we think of the person who's got a radius of 5, then that circumference is 2 pi times by 5, which is 10 pi, which is 31.4 meters. And so the velocity, using the same idea, 31.4 divided by 9.5, gives us a speed of 3.3 meters per second. Okay, so 3 1/3, more or less. So in terms of the actual speed they're going at, in terms of imagine the wind and the hair, the person who's on the outside of the roundabout is going faster than the person inside. If you had a kid and you're going on a roundabout and you're on the sort of the merry-go-round, you might, if you sit on the outside, it's going to be more of a thrilling ride. If you're sitting on the inside track on the hobby horse on the inside, it's a slightly slower speed that you're going at. But we can talk about speed in a different way when we're dealing with something that is rotating. So rather than talking about the literal speed that they're actually traveling at, at any point in time, you can imagine some sort of vector. Okay, what's the speed that they're actually moving forward at? You might think about it in terms of a turn. So, as I said, we're doing a full turn in 9.5 seconds. So, what is the angle? How can we describe a speed in terms of an angle? So, the idea of an angular speed is the angle that it turns per second. So if we think about angular speed as being that angle divided by time, in applied maths we have the idea of angular speed. We use a sort of a roundy sort of looking W. That's the omega. Okay, omega is measured in radians per second, or rads per second. And to think about the example I have here, okay, our angular speed, okay, is going to be, well, a full turn, okay, is 2 pi as a full turn, and that took 9.5 seconds. If I do 2 pi divided by 9.5 seconds, I basically get, give or take, it's 2/3. It's a little bit less. My 9.5 seconds was approximate. It's actually turning at 2/3, i.e. 0.666 recurring. It's 2/3 of a radian per second. Okay. So we could talk about these two objects both having different velocities. The velocity is 5.95 for the 9 meter away person. The person that's 5 meters away is traveling at a speed of 3.3 meters per second. So I have different velocities in terms of a speed, okay, but their angular speed is the same because they're on the same object that's rotating at the same speed. So they have an angular speed that's the same, both of them traveling at angular speed. Omega equals 2/3 radians per second. If we go back to the idea of length being, of an arc being the radius multiplied by the angle in terms of radians. If we think about now speed is a rate of change in length, so length divided by time. So we can think about velocity, which is length divided by time, as being the radius multiplied by the angle divided by time. We tend to write this formula the other way around, so it's usually velocity is equal to omega r, and that would be a fairly standard formula to just be aware of and know. And the key idea to understand, okay, so in a certain amount of time, the velocity over a second, let's say for sake of argument, is that distance traveled in that second. And the angle, the omega, the speed with which it is turning. Okay. So the radius is that radius, the velocity is the distance traveled in a certain amount of time, and the angle that it turns in a certain amount of time is omega. So angular speed, omega, and the actual velocity v relationship is the velocity is equal to omega multiplied by the radius. But in addition to that relationship of velocity and angular speed, it's worth just understanding that angular speed in and of itself, just to repeat. So if you think about the angle divided by time taken, okay, we can also appreciate that as the velocity divided by the radius in the context of v equals omega r. So either of those two relationships are worth appreciating. If you're trying to work out angular speed, sometimes you just know how much of a turn it does in a certain amount of time, so it's angle divided by time. Sometimes you know the velocity and you know the radius. So it's up to you, depending upon the circumstance, what information you're given. So if I have a scenario of something spinning at, let's say 10 revolutions per minute. 10 revolutions per minute. Well, then, okay, 10 revolutions is 10 lots. So angular speed is going to be 10 lots of 2 pi. That's 1 revolution. Okay, per minute. Okay, so that's per 60 seconds. So if I do 10 times by 2 pi divided by 60, that's 20 pi over 60 or pi over 3. And if you work that out on a calculator, it just works out basically as 1.05 radians per second. So I'm hoping that I've been able to give you a sort of little revision of the radian measure in a slightly different context maybe than what you had in your pure maths. And we've introduced this idea of angular speed, a different way of talking about something moving, if it's moving in a circular fashion. And I've gone through a couple of examples where we're using the relationships of the angle, the radius, the length moved, and in terms of speeds. So have a go at exercise 7a on page 125. I'll then be posting up further sort of videos looking at actually things moving. We're going to start by looking at it in the context of a horizontal movement. So if you imagine if you had something on an end of a string and you just manage to make it turn just horizontally, spinning it around a pendulum, rather than pendulum back and forth, it's actually making a circular motion. And then we'll move on to a vertical circle. So if you imagine swinging something around vertically, we'll look at that. And then we'll move on from there, looking at some springs, Hooke's law, and so forth.